Time for us to do some practice with problems involving the mean value theorem. As always, you want to be able to do some practice because there's a really big gulf between seeing something and then being able to do something. And our goal is to get you to the point where you can do something. And the way you do it is practice. It's great to follow along, but do as much as you can on your own. Make frequent use of the pause button and follow along and say, okay, let me see how much I can do. And then you can unpause and say, oh, yeah, I got that. Ah, here's where I got stuck. Ah, now I see it. Okay, now pick up again and keep going. And then you too are going to become a beautiful, wonderful calculus person. All right, well, let's begin. So our first problem, we have the following function, which is continuous and differentiable for all x. So they're just going to tell that to us. We don't have to assume it or prove it. It's like perfect. Boom, here we go. For the interval from -4 to 2, find all values of c that satisfies the mean value theorem. All right, so we're saying, let's check the mean value theorem. See, the mean value theorem says what? So when we're trying to do something for the mean value theorem, we should understand what it says. It says that there is some, possibly many, a less than c less than b, so that the derivative at c, in other words, the instantaneous rate of change at c, is equal to f of b minus f of a over b minus a, the average rate of change. So when we say we want to find any and all that satisfies it, what we need to do is say we need to find all the places where the derivative is equal to the average rate of change. So the first thing for us is going to be focusing on this piece right here. So that means we want to look at our expression. So we want to look at f of 2 minus f of -4 divided by 2 minus -4. And I'm pulling off the -4 and 2 from our endpoints. So that's our a and our b. Now for our function at 2, we would plug it in here. 3 times 2, 6, minus 2 would be 4. So that would be 4. Subtract our function at -4. So -4 is below 1. You use that piece. It looks kind of bad, but good news. We know what f of -4 is. They told us. It's -14. Hey, we'll take it. All right. Downstairs 2 minus -4. Well, that's 6. Upstairs is 18. 18 over 6 is 3. So what the problem is telling us to do is it says, hey, find a place where the derivative equals 3. And actually not just find a place, but find all the places where it equals 3. But we have to be between our endpoints. So now we have our goal. Our goal is we're going to find all values c where we have -4 is less than or equal to c, strictly less than, we don't include our endpoints, less than 2, because the mean value theorem says that we are strictly in between. And our f prime of c is equal to 3. Okay, so our next step is we're going to take the derivative and set it equal to 3. So when you have a piecewise function, you get a piecewise derivative. So what's our derivative going to be? F prime of x would be, well, polynomial, so that's good news for us. 3x squared plus 4x minus 4. Good. Now that's if we're below 1. And I'm gonna come back and visit the less than or equal to. And then it's the derivative of the second one is 3. Oh, that's good news. And that's if we are above 1. Okay, now what happens at 1? Now we kind of know the answer because we were told it's differentiable, which means it has to connect in a smooth way. So the derivative should match. But for sanity's sake, let's just take a quick peek and see if that's true. So what we should do is we should plug 1 into both expressions and see if we get the same. Well, we're going to get 3 in the second expression because it's always 3. In the first expression, when you plug in 1, you get 3 plus 4 minus 4, which is 3. So that says we are coming in a nice smooth way, so that they line up nicely from both sides. There's no like, no, it's nice and smooth. So it is that expression. Okay, good. Now, here we go. We need to figure out when does the derivative equal 0, and we have to look in each piece. So let's start with this piece. So we are looking for things that are below 1, and we want 3x squared plus 4x minus 4 equal to 3. All right, derivative equals 3. I think I may have said the derivative equals 0 a second ago. Derivative equals 3. All right, well, what would that tell us? Well, that says we need 3x squared plus 4x minus 7 equals 0. All right, well, does that factor? And the answer is yes. In fact, we have ourselves a little bit of an advantage because we kind of know something. Remember, we just did a check a minute ago that said, hey, when we plugged in 1, we got 3 plus 4 minus 4 was 3. And so, if you look, that says, oh, look, I think 1 works. So if you plug in 1, 3 plus 4 minus 7 is 0. So 1 is a root, which means x minus 1 has to be a factor. Now that I know one factor, the other one is a freebie. So it would be 3x, because I need x times something to get 3x squared, and plus 7, because I need negative 1 times something to get negative 7. So we are getting x equals 1, and x equals negative 7/3. Now we take a quick peek, and we ask ourselves, do we include these? And the check is, first off, are they below 1? Yes. They can also be equal to 1. And are they between negative 4 and 2? And negative 7/3 is about negative 2.33333. Yeah, that's between negative 4 and 2. All right, so these both make our list. Okay. So, this is a case when we have more than 1 point. All right, well, but are we done? No, because we weren't asked to find some point, or even some points. We were asked to find all the points. So there might be more. I think there will be. Now, let's go to our next stage. So for the next piece, we say, okay, we have 3. So here we go. For which x does 3 equal 3? Now, what's the answer? Well, the answer is 3 equals 3 for all values of x, because it doesn't matter what x is not involved in the expression. Okay, so this holds for all x. Now, which x do we care about? Well, we have to care about x which is above 1, because that's when our derivative is 3, but also we have to be below 2, because we have to be underneath that endpoint. So that gives us all the x between 1 and 2. In other words, there's infinitely many x that work. And so, yeah, it's possible that you can have infinitely many x's that work in the interval. So if we put these two answers together, you can see, because the 1 here fits in nicely, we can change that to a 1 less than or equal to x less than 2. So our final answer would be negative 7/3, comma, and the interval from 1 to 2. And I'll use interval notation, 1, comma, 2, parenthesis. If you don't like interval notation, you can just say this is the same as 1 less than or equal to x less than 2. All right. Well, there you go. Okay. So, yeah, as a reminder, you can have more than one. You can have many, many points which satisfy the mean value theorem. So, okay. Well, on to another problem. All right. Well, find the unique. Okay, this is going to be very different. This time, there's only going to be one unique value c that satisfies the mean value theorem for the function f of x equals arctangent of sine of x between 0 and pi over 2. This is one of my favorite problems. And you might say, yeah, of course you're going to say that, and it involves arctangent. That's part of it. But I think, well, I don't want to give too much away. But when you see the answer, you're like, wow. It's one of those things that you would never think that we could figure out. But we can. All right, so let's think about what we need to do. So the basic setup, we need to figure out all the places, in this case, the one place, where the derivative is equal to the average rate of change. So f of b minus f of a, divide that by b minus a. So we're going to plug in, here are the a and the b. So 0 is our a, pi halves is our b. So we get f of pi halves, and we'll work through that, minus f of 0 all over pi halves minus 0. Now, that would be arctangent of sine of pi halves. So I'm just plugging pi halves in, minus arctangent of sine of 0. Divide that by pi halves. Now, let's work through. Let's start with this one. Sine of 0 is 0. Arctangent of 0 is 0. So this last piece is going to go to 0. All right, good. Now, the next one. Well, it's a little bit more subtle. Let's think about it. Sine of pi halves. Sine of pi halves, this part is 1. Now, what is arctangent of 1? Arctangent of 1 is pi fourths, because the tangent of pi fourths gives us 1. So what we end up with is pi fourths upstairs over pi halves downstairs. And if you clean this up, this would be equal to 1/2. All right, so there we go. We need the derivative equal to 1/2. So now we found what we need to set the derivative equal to. So our next step is, let's find the derivative. All right, so let's look at our derivative. So our function is arctangent of sine of x. So the derivative, following the derivative for arctangent, it's 1 over 1 plus, take the square of what's on the inside, sine squared of x, times that by the derivative of the inside. Derivative of sine is cosine. All right, so we are looking for some angle x, where when we plug that angle into here, it gives us 1/2. Well, there's not really a clear candidate, so we're going to have to keep working on it. So what we're going to do is we're going to set this equal to 1/2. Okay, so now we need to solve. I see fractions, and I don't like fractions. So one of the things I would do is get rid of the fractions. And the way to get rid of fractions is cross multiply. So we're going to cross multiply. That means move the 2 across, move this denominator across. So if we do that, what happens is we end up with 2 times cosine of x equals 1 plus sine squared of x. All right, we're making good progress. Now, where to go next? Well, the problem is we have something which involves cosine and sine. They're close, but they're not quite the same thing. It would be better if they were both the same thing. In other words, they were both sine or they were both cosine. Is there some way for us to rewrite this expression where we can rewrite it in just one of those two functions? So in other words, a trig identity. So is there some way to rewrite this cosine in terms of sine, or this sine squared in terms of cosine? Well, sine squared, that should ring a bell. Beautiful trig identity. Sine squared plus cosine squared equals 1. So we can replace this sine squared by 1 minus cosine squared. And if we do that, everything will be in terms of cosine. So we have that this 1 plus sine squared is really 2 minus cosine squared. All right, well, let's move everything to one side. So if we do that, we'll get cosine squared x, because that's going to come across, plus 2 cosine of x minus 2 equals 0. All right, now, what do we have here? we have a quadratic. Do you see that it's a quadratic? Now, it might not feel that way because it's like quadratic, that's an algebra thing. This looks like a trig thing right now. But think about it in the following way. This cosine squared of x, we could have written it as cosine of x squared, then plus 2 times cosine of x minus 2 equals 0. So you can imagine I could replace cosine x, I could just temporarily give it another name. Y squared plus 2y minus 2 equals 0. And now, all right, we see that. That's a quadratic. And if you've been following along and doing the practice, your next reaction will be, okay, time for us to factor. But this one doesn't factor nicely. Oh my God. Well, you know, it's a life lesson. Not everything will always factor. In fact, most things won't factor very nicely. So, is that it? Is that as far as we can go? No. See, there's a nice little formula that helps us when we have quadratics. Some people call it the quadratic formula. And that helps us solve for it. So what does it say? Well, the quadratic formula, so recall, says if I have something in the form ay squared plus by plus c equals 0, then I can say that y would be negative b plus or minus the square root b squared minus 4ac all over 2a. Now, for us, what does that become? Well, we have our a is 1, b is 2, c is negative 2. So we're going to get that our value for y, negative 2, plus or minus the square root of b squared is 4, minus 4 times 1 times minus 2. So there's a minus, and then it's been multiplied by another minus, which makes it a plus 8 all over 2. Now, if you clean that up a little bit, you'll see the 2 can go into that 2, and the square root of 12, well, I can write that as 2 times the square root of 3. So that means there's another 2 that can cancel. So we get negative 1 plus or minus square root of 3. Okay, so that's the value for y. But remember, y is cosine of x. So by applying the quadratic formula, we come to the conclusion that there's two possibilities. Cosine of x is equal to negative 1 plus root 3, or cosine of x is equal to negative 1 minus root 3. Okay, well, hold on a second. We were told there to be a unique one. This looks like there's two candidates. Can we rule one of them out? And why? Let's look at this one. It seems very negative. Almost too negative. Look at the value. It's negative 1, so it's down low, but then we keep going even further, minus root 3. So it's like really low. But what do you know about cosine? Cosine is going to oscillate up and down between where? Between negative 1 and positive 1. So I cannot get all the way down to minus 1 minus root 3. I can only go as far as negative 1. This value, negative 1 minus root 3, is outside of the range of cosine. And therefore, it's impossible. This can't happen. So we can eliminate that as a possibility. Now, you might say, uh-oh, what about negative 1 plus root 3? Well, the good news is root 3, it's 1 point something or other. I know that's very vague, but I think it's like 1.7 something. And so negative 1 plus root 3 is between negative 1 and 1. It's actually between 0 and 1. So that one's perfectly fine. And in fact, we've now come to the conclusion that the point we seek satisfies the cosine of that value is negative 1 plus root 3. Now, we're not done, but we're so close. We're so close. How do we finally tip the scales to being complete? Well, we got to get rid of the cosine because we just want this value here, what is currently being called x. So how do you get rid of the cosine? You use the inverse of cosine, or arc cosine. So we come to the conclusion that our desired point would be arc cosine of, and I'll just switch the order here, square root of 3 minus 1. And that is the unique location which satisfies the mean value theorem. You never would have guessed that. Ah, this is beautiful. Beautiful. I love it. Great stuff. All right. Well, do another one. All right. So, do a similar problem. Verify the mean value theorem for the function h of t is 2t over 1 plus t squared. And t is going between 0 and 1. So we kind of have the feel for how these problems go. So we're saying, well, we want to take the derivative of this function, and we're going to set it to, in this case, h of 1 minus h of 0 over 1 minus 0. Well, the downstairs is really easy. 1 minus 0 is 1. And the upstairs is actually pretty easy too. Notice that what happens when you plug in 0. 2 times 0 is 0. Aha! So that's going to go away. What is h of 1? Well, it's 2 times 1, which is 2, over 1 plus 1 squared, which is 2. It's 2 over 2. So it simplifies to saying, I just want to know, when does the derivative equal 1? Now, the mean value theorem says there has to be some place between 0 and 1 where this is true. So when it says verify, our goal is we've got to find that point. So we're going to take our derivative and we're going to set it equal to 1. So, well, that means we've got to start by taking our derivative. So the derivative, it's our function here, it's a quotient. So if we're going to take our derivative, we can use our quotient rule. So what's our derivative? We can say the derivative, it's the bottom, 1 plus t squared, times the root of the top, minus the top, times the root of the bottom, which would be 2t, all over the bottom term squared. Okay, we can clean that up a little bit, at least upstairs we can. That would be 2, and then we have plus 2t squared minus 4t squared. So 2t squared minus 4t squared would be minus 2t squared. All divided by 1 plus t squared squared. And that has to equal 1, right? Because we're setting our derivative equal to our average rate of change. Great. Now we just have to solve that formula. Okay, how hard could that be? All right, well, we'll find out. So, we continue. Again, I like to get rid of fractions. So we need to find a place where 2 minus 2t squared is equal to 1 plus t squared squared. Well, this is the same as 1 plus 2t squared plus t to the fourth. And now we can move this over, because it's nice when you have a polynomial to put everything all over to one side. So we have that 0 will have to equal t to the fourth, and then here this is a minus 2t squared, then plus 2t squared is plus 4t squared. Here this minus 2 combined with that plus 1, minus 1. And the reason I say minus 2 because we're going to subtract 2 to bring it over. All right, so now we just have to solve a fourth degree polynomial. We can solve a quadratic, but a fourth degree? I don't know. Oh, wait a second, we can solve a quadratic, right? Maybe this is really a quadratic in disguise. Well, what do we mean? Well, think of this as t squared squared plus 4t squared minus 1. So I can just introduce a nice new name. I can say, well, really, think of this as like x squared plus 4x minus 1. All right, now I have something I can work with. I have this quadratic. Okay, so quadratic formula. All right, well, that seems not so bad. We've done that before, right? So we have the value for x would be negative b, which is negative 4, plus or minus the square root of, well, what? B squared. So that would be 16 minus 4ac. Well, that would be 16 plus 4, because there's that minus 1, makes it minus 4, or plus 4, all over 2. Well, now 16 plus 4 is 20, and that has a factor of 4 in it. And you can pull that factor of 4 out of the square root. You'll get 2 root 5. And then you have the factor of 2 as well. So you can divide the 2 through. So this is negative 2 plus or minus square root of 5. All right, good. So what does that tell us? Well, x is acting as t squared. So we get t squared is either equal to negative 2 plus root 5, or t squared is negative 2 minus root 5. Well, wait a second, hold on. T squared, that's the square of something. I can't square something and be negative. And look at negative 2 minus root 5. That's very negative. Okay, so that we can rule that out. Okay, now that says t squared has to equal negative 2 plus root 5. So we take the square root, and what do we get? Well, we say, aha, that says t is plus or minus. All right, that's the square root of 5 minus 2. Now, does that mean we have two answers? No, careful, because what do we want? We need to be between 0 and 1. The negative 1 doesn't work because it's not between 0 and 1. So our answer, there's actually just one value, and it's the square root of 5 minus 2. And that's the one we're looking for. That says, aha, at this point we have the derivative at this expression is equal to 1. Just like we need it to be, because that's what the mean value theorem says we have. Look at all this good stuff we're getting to do with quadratic equations today. Wonderful, wonderful time. All right. Well, let's do something a little different. So, use the mean value theorem to show that the function f of x, which is e to the 5x plus x cubed plus 7, has at most one root. Now, root, that's where the function equals 0. So, what's the picture? Well, the picture, when you're thinking about it, is we have a function. So, I don't know what the function does, but you can imagine I'm doing something. So, a root is where I'm crossing the x-axis. So, this is a root. So, we want to say it has at most 1. So, what are the possibilities? Well, it has at most 1, or it doesn't have at most 1. Okay, okay, that's good. There's, that's one of those two things has to be true. So what we can do is to say, well, to show it has at most 1, let's show it can't have 2. All right, so suppose it had 2. So suppose that somehow it came back down at some point. So suppose it had 2 roots. Well, what would be true? So here is another root. Well, let's suppose, again, they have to happen at 2 places. We'll say this were at A and this were at B. So if there were greater than or equal to 2 roots, then we let f of A equals 0 and f of B equals 0, and A is not B. Okay, so that says if there's 2 roots, there's 2 places where we have the function equal to 0, which are not the same. How can we use the mean value theorem? Well, let's think about our function here. What's true about our function? Our function has this exponential piece. That's a nice function, very continuous, very differentiable. And the other piece is a polynomial, x cubed plus 7. Again, very continuous, very differentiable. So we can say, hey, our function is 0 at these 2 points, and our function is continuous and differentiable. So by the mean value theorem, what we can conclude is that there must be some c where we have it between A and B with what? F prime of C equal to f of B minus f of A over b minus a, well, that's equal to 0. So if there were two roots, there would have to be some place where the derivative is equal to 0. All right. Well, so what's our derivative? Let's look at our derivative, f prime of x. Well, the derivative of e to the 5x is 5e to the 5x, because it used the chain rule. The derivative of e to something is e to something times the derivative of that something. So that's where the 5 is coming from, the derivative of the top. Derivative of x cubed is 3x squared, and the derivative of 7 is 0. So it goes away. Now think about our pieces here. 3x squared, well, what do we know about 3x squared? The x squared kind of tells us this part, it's always greater than or equal to 0. And what do we know about the exponential function? It's always, always positive. E to anything is positive. Doesn't matter what the input is. So this is definitely a positive value, and therefore our derivative is positive. Wait a second. That's impossible. See, this says if there were two roots, there'd have to be a place where the derivative is 0, but this says the derivative is never 0. So our conclusion is this is impossible. All right, because there's that inconsistency. I can't have something be always positive, but somewhere be 0. So what's the flaw? Well, the flaw is somewhere we made a mistake. Where was our mistake? Our mistake was our assumption. So this must mean that this assumption is wrong, because everything else we did built off of that assumption. And so now we said, okay, so it's not the case there are two or more roots. And so that means there's at most one root. Now, what actually is happening with this situation is our derivative is saying something. Think about what our derivative is telling us. It says our derivative is always positive. So in terms of the picture, what that means is that if you think of the picture, it means that the function always is moving uphill. So if our function is always moving uphill, I can't hit 0 and then go back downhill to hit it again. No, once I cross 0, I'm always going to be going further and further up. So this gets into the behavior of the function, which we're going to talk about in a session very soon. All right, well, but that's for another session. Okay, well, time for one more problem. All right, so we're given that f of x is differentiable from 0 to 7. In particular, that means it's continuous, it has a nice derivative. We can apply mean value theorem, which is what we're learning today. So we should be able to use mean value theorem here. We know something about the behavior of the derivative. Between 0 and 3, our derivative is between 2 and 5. And between 3 and 7, our derivative is between -1 and 3. And we also have some information about how we start at 0. It says we start here at 3. So the question, determine the possible values for the function at 7. All right, so how does the mean value theorem come into play? Well, let's think about sort of our intuition, and then let's see if we can justify our intuition. So we're going to do a quick sketch here. So let's say here, let's say this is at 3. So we know we start off at 3. So we have that initially from 0 up to 3. So here is from 0 to 3. What's happening is that our rate of growth, and that's how we can think of derivative. What's our rate? How fast are we changing? The idea is it's between 2 and 5. So let's try the following. Suppose we were to start at 3 and go on a line that had a slope of 2. So if you did that, so starting at 3 and had a line that had a slope of 2, you went over by 3. That would mean you went up by a fair amount. So you'd have gone up by 6, right? Because, slope of 2, changed by 3, you'd gone up by 6, you'd be up to 9. On the other hand, if you had a slope of 5, well, what would happen? Well, you'd go up to 15, right? Because if your slope is 5, that's how much you change, and over by 3 would get you up by 15 more, which would put us up here at 3 plus 15 would be 18. Now, I claim that whatever the function does, it always has to stay inside of here, between 0 and 3. And in particular, we cannot leave this little triangle. Why not? Well, let's suppose somehow we did leave. So suppose we got somewhere over here. Well, what would happen is, according to the mean value theorem, you would look here and say, well, let's look at the slope. The slope, it's below 2. And therefore, somewhere in between 0 and 3, we would have to have the situation where our derivative would have to be below 2. And we're told, no, it doesn't happen. Our derivative is never below 2. See, whenever we leave this triangle, we're going either our rate of growth is dipping below 2 or we're dipping above 5, which is impossible. So our function has to stay in here. Even if it stays in here, there's still not complete freedom, but it has to do something along those lines. Now, what does that say? Well, it means by the time we hit 3, we're somewhere between 9 and 18. Okay, so we've narrowed it down so that we're somewhere in that range at 3. But that's the halfway point. Now, what happens next? Well, the next stage is to get up to 7. So, well, you can imagine, all right, what can I do? Well, it depends, right? Because you could be anywhere between 9 and 18. You don't have any information other than you're somewhere between 9 and 18. So, well, we can say it doesn't matter where we are. If we start here, what do? Well, you again form a little sort of cone here. You say, my growth is bounded below by -1, so I'd have a slope of -1 going down, or I'd have a slope of +3 going up. So there's this little tiny cone here. So that would be at that particular point that I'd have to stay in between. But that's for any arbitrary point, I can make such a cone. So now what I do is I can imagine duplicating that cone all the way up and down. And so what we end up with is we end up that we have to stay somewhere in this portion here. So this bottom part here, that's a slope of -1, and in the top part, that's a slope of +3. I'll go ahead and mark what we did over on the first part as well, just for reference here. So here we have a slope of +5, and then here we had a slope of 2. So, moral, where are we at so far? Well, we said, look, initially from 0 to 3, we have to stay inside the purple. We're going to end up somewhere along here, and then wherever we go, again, we get this new cone of growth, places where we could go, but we could go anywhere where we start, so we get to shade a lot. There's so many places we could be. But where can we possibly end up? Well, we say what happens if I start at 9, slope of -1, and then I went over by 4, because that's 3 to 7 is 4, that says that this place right here would be at 5, all right? Because I can go down by 4. On the other hand, I started at 18, I had a slope of 3, and I go over by 4. That means I can go up by 3 times 4, which is 12. So I can get all the way up to 30. And I have to be somewhere in between these two. So I can come to the conclusion that 5 is below f of 7 is below 30. and now I can limit it down. Can I go any further? I actually can go a little tiny bit further. Okay, let me ask you the question. Is it possible for me to get to 5? The only way I could get to 5 would be to do what? I'd have to be hugging the very bottom here. Because if I got even just a little bit up here, then I'd be stuck. I could not get down to 5 because I would only be able to get, there'd be a little gap. So I'd have to follow the very bottom edge. And similarly, I'd have to follow this very bottom edge, which would mean what would be true at that point? I'd have a not differentiable. So I can't hit 5. I can get as close as I want to 5 because I can get just barely over, and there I can make a very tiny smooth transition. You can be very smooth and still be very close to something that looks like you have a sharp turn. But you can have a very tiny corner that gets you around that sharp turn. So we can throw out 5 by the same reasoning we can throw out 30, and therefore, if we are going to say what are all the possible values, it has to be any value between 5 and 30. And that's it. That's as much as we can say. Well, that's actually not so bad. That gives us a fair amount of information. So if we can say, for instance, our function can't be 2. We know that's not possible. All right. Well, this is kind of getting to sort of like, if I understand my derivative, I understand my growth, and I can bound my growth, which helps me rule out where my function can and can't be. So it's we're getting to sort of the understanding the behavior of the functions by understanding the derivatives. And that's going to be a big theme in our upcoming sessions. But for now, thank you for coming to the practice, and I hope you have a great day. Hey guys, thanks for sticking around. It occurred to me that maybe my explanations are not the most convincing on this last one, so I wanted to give you just one other alternate point of view and seeing how this connects to the mean value theorem. So let's try just to focus on what's happening at 3. So let's set a mini goal. And the mini goal is to say, what can we say about f of 3? And, well, what we can do now is we can say, hey, let's use the mean value theorem. So we know that this value, f of 3 minus f of 0 over 3 minus 0, has to equal f prime of c, where what's true? Where c is some constant between 0 and 3. But what do we know about our derivative between 0 and 3? It's between 2 and 5. Now, if you multiply out by 3, you can get that 6 is less than or equal to f of 3 minus f of 0, which we know is 3. So minus 3 is less than or equal to 15. And now if you add 3, 9 is less than or equal to f of 3 is less than or equal to 18. And now, lo and behold, that's exactly what we were saying here. So once you know what f of 3 is, you say, okay, you have f of 3 is between 9 and 18. Well, what about f of 7? Well, now you can do a very similar process. You can say, hey, I can look at f of 7 minus f of 3 over 7 minus 3. Well, again, that's equal to the derivative somewhere, and that's between negative 1 and positive 3, because it's the derivative somewhere between 3 and 7. So it's between positive 3, negative 1. Now, do the same process. Clear your denominator. In other words, multiply by 4. So you can say negative 4 is less than or equal to f of 7 minus f of 3, which is less than or equal to 12. Right? Okay, now what do you do? Well, that says whatever the value for f of 7 is, that has to be less than or equal to 12 plus f of 3 and greater than or equal to negative 4 plus f of 3. And so what you're seeing here is you're seeing these individual little pieces coming off. So what's the punchline? Well, I now have a bound for f of 3, and now I can say how big f of 7 can get. So finally, if I say, well, look, worst case scenario, f of 7 is at most 12 plus the worst case scenario for f of 3 is 18. So I can conclude that f of 7 has to be at most 30. And that would be, of course, worst case. Worst case on the other end, negative 4 plus f of 3, but the smallest f of 3 can be is 9. So this would be negative 4 plus 9, which is 5. And then, of course, we still have our same corners argument. So anyways, this is just a different alternative take, which makes it a little bit more explicit about saying, hey, how can you use the mean value theorem directly? Understanding the way things grow is, of course, also very useful and really will be an important idea in the upcoming few sessions. All right. Again, thanks for sticking around to the end. Have a great day.